Hi, I'm Mike Yawn, a Senior Solutions Architect with Hazelcast, and this is TellUvision. In this episode, we look at partitions, the basic unit underlying how Hazelcast stores your data. All data in Hazelcast is stored in partitions, but not all data structures are partitioned. Now, what the heck does that mean? To understand it, let's look at the three types of data structures in Hazelcast. Data in partitioned data structures is divided into multiple pieces, and those pieces are then distributed among cluster members. Partitioning is great when access to the structure is somewhat random, as with the hash map. Partitioning helps us efficiently manage large data structures by spreading them across the entire cluster. Partitioned data structures include IMaps, multimaps, caches, and map journals, as well as the upcoming vector collection. Replicated data structures are structures whose contents are duplicated on each cluster member. That's useful for smaller reference data that might be used for frequent lookups. Replicating these means that any member can access them locally without a network call. But updates are less efficient than a partition structure since every modification must be replicated to each member in the cluster. Replicated data is still stored in partitions. While a partition structure will have a primary copy on one node and backup copies on one or more other nodes, replicated copies are equivalent. There is no special primary copy. CP data structures like semaphores and locks are somewhat like replicated structures in that they are replicated across multiple members, but they're really their own thing and play by their own rules. We'll cover the CP subsystem in future episodes. Other structures like sets, lists, and queues are kept intact on a single member. They reside entirely within a single partition. Operations on these structures can be implemented more efficiently because the data is co-located rather than spread around the cluster. Here's how data gets assigned to partitions. If we are putting an entry to a map, we start by hashing the key of the map entry. This gives us a numeric result. We then mod that result by the partition count, and this gives us our partition ID. We'll look up the partition ID in the partition table, which is distributed to all cluster members and clients. That lookup tells us which member currently hosts the primary copy of that partition. We can then send the entry to the operation queue of the target member and partition, where the partition thread will pick it up and add it to the map. Now, your first thought might be that the number of partitions will equal the number of nodes, but partitions in Hazelcast have several important functions besides just acting as storage buckets. Hazelcast ensures high performance by enabling multi-threaded access to data structures like an IMAP without the need for locking. Each partition has a dedicated thread, ensuring thread safety without explicit locking mechanisms. Consequently, operations for a specific key are queued and managed by the partition thread where that key resides. Increasing the number of partitions allows for more concurrent operations. For example, in a 5-node cluster that only had 5 partitions, each node utilizes only one thread for partition operations. But with 100 partitions, up to 20 concurrent operations per node are possible, provided there are sufficient CPU cores. Thus, it's essential to set a partition count large enough to fully utilize CPU cores. While concurrency is a significant factor, it's not the sole consideration when determining the optimal partition count. Elastic scalability in Hazelcast clusters means that when you scale up from, say, a 5-node cluster to a 6-node cluster, the new node doesn't sit idle. Data rebalancing begins immediately, ensuring that each node holds an equal share of data. During rebalancing, entire partitions, not individual entries, are moved between nodes, maintaining the key to partition assignments while redistributing partition ownership. For efficient rebalancing, partition sizes should ideally range between 50 to 100 megabytes. Optimizing this partition size is crucial in determining the appropriate partition count for your cluster. The default partition count of 271 is well suited for starter-size clusters, such as a 3-node cluster with 8 gigabytes of heap per member. Using Hazelcast's high-density memory feature, an Enterprise Edition feature, allows storing up to 200 gigabytes per node outside the Java heap, minimizing garbage collections pauses. For such configurations, a larger partition count, starting from 5,009 partitions, is recommended to match the increased memory capacity. Let's recap. Some data structures, in particular the IMAP, are partitioned with partitions distributed across all nodes. Hazelcast also has replicated structures with all content on each node, and structures that are distributed but not partitioned. Hazelcast uses the partitioned architecture to achieve lock-free concurrency and to enable features such as elastic scalability. That's all for today. We will see you next time on a future episode of TelUvision.